Hi there, thanks for checking out Raylene Maths. In this video we're going to take a look at polynomials from the point of view of their linear factors and their zeros. So our objective is to look at the factored form of a polynomial and from the factored form see what the zeros or the x-intercepts are of the graph. We've got some different knowledge and definitions and some skills that we'll go through in the video. Okay, as a warm-up here, let's consider a quadratic polynomial y equals 4x squared plus 4x minus 15. And we want to first work out the quadratic discriminant. Now recall that the quadratic formula for y equal to 0 gives us that ax squared plus bx plus c equals 0. And because we have x in two different terms in the equation, it's difficult to solve. The quadratic formula then is a formula that gives us the value for x. It's a rearrangement of this equation where x is occurring only once in the equation. And the radicand, or the stuff under the square root, in the quadratic formula is called the quadratic discriminant. So here the quadratic discriminant, or d, is equal to b squared minus 4ac. Then with a equal to 4, b equal to 4, and c equals negative 15, we end up getting 4 squared minus 4 times 4 times negative 15. And here I'm going to work this out as 16 minus 16 times negative 15. So 16 negative times negative is positive, and this is 16 times 15. And I'm not going to multiply these together first. Instead, I'm going to see that there's a 16 common factor. And if I take that 16 out, then technically this is 16 times 1. I will be left with 1 plus 15, which is 16. And so 16 times 16 is 16 squared, which is 256. But I'm less interested in the fact that this is 256 and more interested in the fact that 256 is a perfect square, because that discriminant goes under the square root sign. And when I take the square root of a perfect square, I get a whole number. Because we have the discriminant is a perfect square, that tells us that we are able to simplify without having, in the quadratic formula, without having any radicals. And therefore the quadratic expression for 4x squared plus 4x minus 5 can be factored. And so this is really what a perfect square of a discriminant tells us. And so because this quadratic expression can be factored, let's solve for the zeros of the function by factoring. So the zeros of the function is just another way of saying the values of x that make or such that the function, or the function value, or the y values are 0. And so substituting y equal to 0, we get 4x squared plus 4x minus 15 equals 0, and we know that this can be factored. We know this can be factored because the quadratic discriminant's a perfect square, which means that we have no radicals left in our roots or zeros or x-intercepts of the quadratic function. So when we factor, we can try lots of different methods, but we should have some strategies of trial and error or separating the middle term. And so here we end up getting that the 4x squared can factor into 2x times 2x, and the negative 15 can factor into 5 times 3, and we need a middle term of positive 4x. And the 5 and the 3 have to have opposite signs because this is a negative here. And so we end up wanting the bigger of the outer product and the inner product to be positive. So we're going to get 5 times 2x is 10x, and 2x times 3 is 6, so I want negative 6x. And so this gives me the 4x squared plus 4x minus 15, and from here we end up getting that either 2x plus 5 equals 0, or 2x minus 3 equals 0, and as a result, x either equals negative 5 over 2 or 3 over 2. The next question is asking for us to identify the terms polynomial as a polynomial expression, equation, or function. And so in the case where we have both x and y, we have a polynomial function. So while we might just say polynomial, it might refer to being a function or to an equation, such as the second case where we have only one variable, or an expression, which is where there is no equal sign at all. And so in the third case, we have the same terms of the polynomial, but in this case, this is simply an expression. So to be clear, any one of these three might be written or expressed as a polynomial, but they are specifically polynomial function, equation, and expression. In number 3, we want to write the polynomial. Each of these is functions. We want to write them in factored form from the standard form. Recall that the standard form has the leading term first, which is the term with the highest exponent on x, and then all the terms are in decreasing exponent on x form. So we notice that each of the terms on the right-hand side has a common factor of x, and when we factor that out, we get x squared minus 4x minus 21. So we end up getting a linear factor, and a factor is something joined by multiplication, times a quadratic factor. And so we want to factor into linear factors. So we further factor the quadratic, we get y equals x times 2 linear factors. X squared factors as x times x, negative 21 will factor into one positive and one negative number. And so the factors are going to be negative 7 times positive 3 to give negative 21. And then just to confirm, the middle term is going to give us positive 3x minus 7x for a total of negative 4x. And so we have the full factoring here, x times x minus 7 times x plus 3. The next case, we have a quartic polynomial because the degree is 4, and quartic comes from the word quartet, meaning 4. And we notice that, again, we have a common factor of x squared. So we have a quadratic multiplied by another quadratic, and this second quadratic has the form of a squared minus b squared, which is a difference of 2 squares. The difference refers to the fact that we have a minus sign, and then the squares come from the fact that the first term, a squared, is somebody squared, as is the second term. And so we factor the difference of squares as conjugates, a plus b times a minus b. The word conjugate means we have the same two terms but opposite signs in between. And so from here, we can further factor the 9x squared minus 25 by noticing that 9x squared factors into 3x times 3x. We have the same two terms but opposite signs in between, so we have a positive and a negative, and 25 factors into 5 times 5. So we have a quadratic. Technically, we could factor that as x times x, but we can leave it as x squared times 3x plus 5 times 3x minus 5. Here we have a few equivalent statements about the polynomial p of x and a real number r, and we choose r because it's the first letter of the word root. These statements are equivalent. Just to be clear, this is a polynomial in standard form. It's expanded, and we have the exponents on x leading with the biggest exponent and in decreasing exponent form or order. Then these numbers a subscript n minus 1, a subscript n minus 2 are the coefficients of the polynomial. Now in the past, when, for example, we had a quadratic function, we just used letters a, b, and c. And for a linear function, we actually used m and b. So to follow the pattern of the alphabet, we could have called this ax plus b. Now we're not using a, b, c here because we don't know what n is, and if n is bigger than 26 for all the letters in the English alphabet, or even 25 because we couldn't use x as one of the letters, we need to have another naming system, so we use these subscripts. It's a bit confusing, so since we'll probably never get x to the exponent of 25 or 26, you can probably just think of it as a, b, c for now. So these statements are equivalent about the polynomial and a real number r. If the polynomial evaluated at this x value equal to r is equal to 0, this means that we have an x-coordinate of r and a y-coordinate of 0, and anytime y is equal to 0, we have an x-intercept of the polynomial graph. Then x equal to r is a 0 because by definition of the word 0, this is a value for x that makes y equal to 0, and we saw that that was the case, y was equal to 0. So we would simply say that x equal to r is a 0 of the polynomial function y equals p of x. If we were to substitute y with 0, we would get a polynomial equation, p of x equal to 0, and then we would say that x equal to r is a root of the polynomial equation. And then if x equal to r is a root, we know from the zero product property, let's just go back to an example, if we had a quadratic that had been factored and set equal to 0, then we would say either x minus 1 equals 0 or x minus 2 equals 0, and therefore x equals 1 or x equals 2 gives us the zeros or the roots of the equation. And so to work backwards, we would subtract 1 from both sides and set that equal to 0. So what's happening here is if x equal to r is a root, then we could subtract r from both sides of the equation, and then we would get x minus r equals 0, and then the x minus r is the factor, or the linear factor, because the highest exponent on x is equal to 1, so we have linear. Okay, so those are just some equivalent statements. Just like calling polynomial expression, polynomial equation, and polynomial function all just polynomial, we sometimes mix up the words 0 and root and x-intercept. So this is the formal way that we will talk about them. Now, just to be clear, a term such as these things in the standard expanded polynomial equation are things that are joined by addition or subtraction. And a factor is something that is joined to another factor, so they're variable expressions that are joined by multiplication. So we are now going to be talking about going from standard form, like we have here, this expanded form, into factored form. I'm just going to move those out of the way. And factored form means we have things joined by multiplication. So the factor theorem is a special kind of rule, I guess, or a special bit of information that says if x equal to r is a zero of the polynomial function, in other words, it's a root of the polynomial equation when y is set equal to 0, then the linear expression x minus r is a factor of the polynomial expression. So really it's just a theorem that says all of these things are equivalent. And so if we have a 0 of x equal to negative 3, then when we add 3 to both sides, we would get x plus 3 equals 0, and so therefore the factor would be x plus 3. Similarly, if x equal to 0 is the 0, then subtracting 0 from both sides, we get x minus 0 equals 0, and we don't really need to put this minus 0, and we get that the factor is just x. Now we could say the factor is x minus 0, but we can simplify that to x. And then in the last case, I'm going to use a bit more space, we subtract 2/5 from both sides of the equation, so we get x minus 2/5 is equal to 0. And therefore we can say that the factor is x minus 2/5. Now, we could also take both sides of that equation and multiply to clear the fraction. We could multiply by 5, for example. And so that would give us 5x minus 2 is equal to 0. And of course, if we worked backwards from this to solve, we would get x equals 2/5. So it's also possible that we could say that the factor is 5x minus 2 if we wanted a factor that didn't involve any fractions. So now we're going to work backwards. We're going to write the equation of a polynomial in factored form from its zeros. So if we have the zeros, we know that x equals negative 3 or x equals 2/5, and we're going to work backwards to say that x plus 3 equals 0 or x minus 2/5 equals 0. And from here, we're just working backwards from the zero product property to say that this times this, those two factors of x plus 3 and x minus 2/5 multiply together to be 0. So normally we start from here and we go in the reverse. We're just going in the opposite direction of normal. And since we wanted to write a quadratic function, we actually realized that we had set y equal to 0, and we are going to write the quadratic function as y equals x plus 3 times x minus 2/5. Now, this isn't the only quadratic function that has these zeros. So notice that we didn't write the equation of the quadratic function, but write the equation of a quadratic function. And the reason is we could have a leading coefficient of a, which is 1, such as it is here, or any other value, and it would not impact what these solutions for x are when y is equal to 0. So in this particular case, we want to write the quadratic function with no fraction coefficients. In other words, we want to get rid of this 5 here. If a were equal to 5, then we could multiply that through the brackets. So we can have y equals 5 times x plus 3 times x minus 2/5. And in that case, we would take the 5 and we would multiply it through either the first fraction or the factor or the second factor, but not both. The reason is if you have 2 times 3 times 4, that equals either 2 times 3, which is 6 times 4, which is 24, or it equals 2 times 4 times 3, which is equal to 8 times 3, which is 24, but it doesn't equal 2 times 3 times 2 times 4, because that would give us 6 times 8, which is 48, which is 2 times too big. The reason it's 2 times too big is because we've multiplied the 2 twice. And there's the factor of 2, that is the extra doubling. In other words, the 5 only multiplies through the first bracket or the second, and I would like the 5 to multiply through the second bracket because that would help us to get rid of the denominator, so we will no longer have any fractions. So we would have y equals x plus 3 multiplied by 5 times x minus 5 times negative 2/5. Now it said no fraction coefficients, so presumably we would want to expand this and put it into standard form. So we would get 5x squared. The outsides multiply together to give negative 2x. The insides give us 15x. And then lastly we get minus 6. So we get 5x squared plus 13x, and then subtract 6. And we want to do a similar thing, but this time come up with a cubic polynomial with the zeros of 1, 2, and 3. First of all, in factored form, we would have x equal to 1, or x equal to 2, or x equal to 3. So that gives us the factors of x minus 1, or x minus 2, or x minus 3. The reversing of the solving means we have to subtract 1, subtract 2, and subtract 3. And doing the opposite is why we have the opposite sign here that we've seen so often through our linear and quadratic equations. Then to come up with the cubic polynomial, it didn't specify to come up with an expression of an equation or a function, so we could just say that the cubic polynomial p of x would be the first times the second times the third factors. And so then we want to come up with the standard form, which means we want to expand. Now when we expand, we want to choose to multiply together 2 brackets at a time, so I'm just going to take the second 2 brackets first and leave the x minus 1 to be distributed later. Now we could use the box method for this, or we can just make sure to be very careful with our algebra. We multiply the first times the first, which gives us x squared. Now I'm going to multiply the outside and the insides together at once. So we get negative 3x minus 2x, which is minus 5x, and then we get the last times the last, which is negative times negative, or positive 6. And then I'm going to take the x and I'm going to multiply it through all of the terms, and I'm going to write those answers in red. So I'm going to get x cubed minus 5x squared, and then x times 6 is positive 6x. And then I'm going to take the negative 1 and multiply it through all of these terms in green. And I notice that negative 1 times x squared is negative x squared, so I'm going to line that up underneath the x squared column. Negative times negative is positive, and we get 5x, which lands in the right x column, and negative times positive is negative, and then we have a 6. So altogether, we see that we have one term for the cubic and the constant, but 2 terms each for the quadratic and the linear. So we get a total of x cubed minus 6x squared plus 11x minus 6, and that would be our standard form of the polynomial. Now we're going to come up with the polynomial graph using the zeros and all the rest of the information that will help us to sketch the graph of this polynomial. So we can first of all come up with the x-intercepts from the factored form very easily. If we were to set y equal to 0, then we would end up with x plus 1 times x minus 1 times x minus 3 all equal to 0. And by the zero product property, either x equals negative 1, so I'm going to write it like this, x equals negative 1 or positive 1 or 3. And from here we can write the coordinates as ordered pairs, negative 1 comma 0 or 1 comma 0 or 3 comma 0. So I'm going to plot those points on my grid over here. And I'm then going to come up with the y-intercept, which is a value for y when x is equal to 0. Now I don't have to expand this to get the y-intercept, I simply need to substitute 0 for x. And so we get 0 plus 1 times 0 minus 1 times 0 minus 3, which is a total of 1 times negative 3, which is positive 3. and therefore as an ordered pair we have 0, 3. Now this is just a coincidence that we have a same x and y intercept. It doesn't always happen that way. Whenever we're sketching, we should label the x and y axes and put arrows on the ends. Now we also want to come up with the leading term so that we can sketch the end behavior and then identify these arrows here. So to come up with the leading term, we would need to expand this. But I don't actually want the full standard form, I just want the first term. So as we saw in the previous question, when we were expanding, we could get the leading term coming from, as we did here, the leading term of the first factor multiplied by the leading term of the second factor gave us the leading term. So we can just work with the leading term of each of the brackets. And in this particular case, we're going to have the leading term from the first factor times the leading term of the second factor times the leading term of the third factor. And that's going to give us x cubed plus some other terms. I'll just put plus dot dot dot. So the leading term is 1x cubed, and the polynomial ends then will look like a y equals x cubed graph. On the left end, the graph goes to the left and down, and on the right end, the graph goes to the right and up. So it will look very much like the y equals x cubed graph, which has a shape like this. But we're only focusing on the ends because the x-intercepts mean that the middle behavior looks different because we've got different x-intercepts. And so what this says is as x goes to the left, y goes down. So as x approaches negative infinity, y approaches negative infinity. And then on the right end, as x approaches positive infinity, as x goes to the right, the graph goes up. So as x approaches positive infinity, y approaches positive infinity. So we know that those ends need to be for this graph as well, which means that we're going to come this way, reach this point, somewhere turn around and come down, turn around and come up again. So I'm just going to move those end behaviors for now and maybe fit my graph like this. Now, one misconception would be to assume that this y-intercept point is the turning point. It may be, but it may not be. And the chances are we didn't find one point that just coincidentally happens to be the turning point. So I'm actually going to try to put my turning point somewhere other than here. And in fact, what is something that we do not know how to sketch about the graph? We do not know how to sketch the turning points. So unlike parabolas, quadratic polynomials where we have a formula and we can work out the vertex h comma k, we don't know the turning point of other polynomial functions. And in fact, that's going to be the realm of calculus for learning how to come up with the coordinates of these turning points by hand. So we are going to need to use graphing technology to figure out these turning points. For now, we will just approximate them, and if we have it wrong, perhaps maybe the turning point needed to be on the other side of the y-intercept. That's okay for our purposes for now. We'll do our best to figure out where the x-intercepts are, the y-intercepts are, and what the end behavior looks like, and then we will not worry so much about exactly where those turning points need to land. Another example is that this turning point might be much lower, so we don't either know the x-coordinate or the y-coordinate of those turning points. Okay, let's try another example. Fully factor the given cubic polynomial and then sketch its graph. So the first thing we notice is that we have a common factor of x that has been factored out, and we have difference of squares, which we can factor as 2 times 2, opposite signs, and then x times x. I also notice that the 2 minus x is the same as negative times x minus 2. So I'm going to take that negative and factor it out here, and then I will have 2 plus x, which I can rewrite as x plus 2. I like to lead with the x, and then x minus 2 from the red factor. And so from here, we can also come up with the leading term. We can do it at the beginning because we are closer there. We take the leading term of the first factor multiplied by the leading term of the second quadratic factor, which gives us negative x cubed. And so a sketch of the ends will be the opposite shape as what we had, and as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches negative infinity. So we will use that plus the coordinates of the y-intercept and the x-intercepts to help us sketch the graph. To get the y-intercept, we set x equal to 0, and so f of 0 is going to be Now you can use it either from the fully factored or the partially factored form. I will go back to the partially factored form because it's a bit easier. We will have 0 times 4 minus 0, which is 0 times 4, which is 0. So as an ordered pair, the y-intercept is located at 0, 0. Then we also have the coordinates of the x-intercepts. Well, we have 3 factors. I'm just going to rewrite them again. Negative x times x plus 2 times x minus 2, and we set all of that, well, we set y equal to 0, and then by the zero product property, either negative x equals 0, or x plus 2 equals 0, or x minus 2 equals 0. And therefore, multiplying or dividing by negative 1 gives us x equals 0, and then subtracting 2 gives us x equals negative 2, or finally x equals 2. So we have our 3 x-intercepts for the cubic polynomial. We can't have any more than 3 x-intercepts because we can't have any more than the degree of the polynomial. And we know the end behavior is coming down first, going through the intercept, turning around, coming up, turning around, and going down. And so we have the right number of x-intercepts to turn around for the end behavior. Now we might get that a little bit tidier, but again, we don't know exactly where the turning points are, so we will leave that for technology, and for now we will just do our best approximation to make the graph look smooth and to fit all of the information of the equation. Okay, well, when we're talking about turning points, we have some new names for them. In the case of a parabola, we just called it a vertex, but we did identify whether the vertex was a maximum or a minimum based on whether the a value gave us a concave up or a concave down parabola. So in general, whenever a graph changes from going up, which is increasing, to going down or decreasing, the turning point is a relative maximum. So for example, here the graph is going up or increasing, and then the graph is going down. So at the point where the graph changes from going up to going down, we have a relative maximum. Furthermore, whenever the graph changes from going down to going up, in other words, changing from decreasing to increasing, the function does so at a relative minimum. And so from here we're going to use the terms relative maximum and minimum. Relative just means that it's the y value which is the highest in a local or zoomed in neighborhood relative to other points nearby. The reason that this point is not an overall or absolute maximum is because if you take a look over here, the graph keeps going higher and higher, so the y values will reach a higher height than the height at this relative maximum. Same thing for the relative minimum. And it's important to note then that we talk about the relative maximum or minimum point, which has an x and a y coordinate, but whenever we want to talk about the relative maximum or minimum value, just like the 0 is a function value of 0, so here the relative max or min value is the function value, which is the y coordinate. So if we're talking about a point, yes, we give both x and y coordinates for the max and min points, but the specific maximum or minimum value is the y coordinate. So we've found the coordinates of the turning point or the vertex for parabolas by hand, but in general we can't do this for most graphs. We're going to have to use technology, and then when we get to calculus, we learn how to find the coordinates of the turning points for all functions and not just parabolas by hand. In number 9, we're going to use Desmos, and you can use your personal handheld graphing calculator to find the relative maximum and minimum of the two functions that we saw in the previous question. So let's take a look at these. And so for the first one, all you're going to do is trace along in Desmos, and generally this technology will have a clicking or some kind of locking onto that point. So we see that the location of the relative maximum point is negative 1.555 and then 3.079. So we'll just record that here. The relative maximum, I'll put it in red. I'll put it in blue because I did it in the blue graph. Negative 0.155, comma 3.079. And these are approximate because there is a lot of, well, not perfect values or not exact decimal values here. Then if we trace along to the relative minimum, it was kind of already there as a gray point. So you can lock onto it and you can see that that point is 2.155, comma negative 3.079. There seems to be some interesting similarities in the numbers here. Makes it easy to copy and put it over here. 2.155 and then negative 3.079. Okay, we can do the same thing for the other graph. I'm just going to graph, oh, I think I did that one in red. Anyway, let me just pretend I did it in blue. Oh, it doesn't matter. And I'll do this one now. And so we can see that the relative minimum value is negative 1.155. Seems to be a lot of similar numbers here. That's just the way it is. It's just a coincidence for this particular pair of graphs. But again, it makes it easy for me to record them. Negative 1.155, comma, I actually find that really interesting that the numbers are so similar. And then negative 3.079. And then over here we end up getting 1.155 and then 3.079. I think if I had tried at random to pick two functions where the decimals were the same for the maximum and the minimum points, I wouldn't have been able to do it. Okay, in number 10, we're asked to determine the relative maximum and minimum values of this cubic polynomial. So again, we're not meant to do it by hand, so we will use technology and just type that into, let's say, Desmos. So we have another function. I'm just going to write it as y equals x cubed minus 5x squared minus 24x. Let me just double check that that's correct. 1x cubed minus 5x squared minus 24x. And I can't see the maximum and the minimum, so you can either click zoom in or zoom out, or you could adjust the window dimensions. You can make the y values go a bit lower. Let's say negative 100, and I think I said negative 1001. So negative 100 to 100. And if that's not big enough, well, it is for the relative maximum, but it's not for the relative minimum. So I'm just going to go a little bit smaller, maybe 150, and there I can see it. And so again, we have the fortunate feature of being able to lock on here, and we get negative 1.616, comma 21.507. Now notice that the question in this case asked for the maximum and minimum values, the relative maximum values. That means that we only want the y-coordinate. And so the relative maximum has a y-coordinate of 21.507. So the relative max value, or just relative max, equals 21.507, and the relative minimum, and again, these are approximate, they're not exact values, so we could use the approximation symbol instead of exact. And the relative minimum we see is located at this point, and it has a y-coordinate of negative 120.025. Negative 120.025 for our relative minimum value. Polynomials don't just have linear factors that are raised to the exponent of 1, or zeros that occur once. We refer to the multiplicity of a zero, x equal to r, as the number of times that that zero or x-intercept occurs or is repeated. And the number of times that that zero occurs is the same number as the exponent k on the linear factor that the zero came from. So if x equal to r is the zero, then the factor is x minus r, but it could also be raised to an exponent of k. In other words, we have this factor x minus r k times, and multiplicity or multiple means number of times. So let's consider a polynomial here, y equals x squared times x plus 2 cubed times x minus 1. And we can come up with the leading term of the polynomial by taking the leading term inside each bracket, but now we have to consider in x plus 2, the leading term is x, but it needs to be cubed. So we're going to have x cubed, and then we're going to get x to the exponent of 1 here. So if we were to expand only the first term from each bracket, we would get x squared times x cubed times x to the 1 plus some leading terms, some other terms, some lower order or lower degree terms. And then x squared times x cubed times x to the 1 is equal to x to the 6. And so a polynomial x to the 6 has end behavior that has both ends going up. In other words, as x goes to the left, y goes up, and as x goes to the right, y also goes up. Now, had there been a coefficient in front of x squared that was negative, then we would be vertically reflecting and the graph would be going to the left and down and to the right and down. But that's only if we had a negative in front of this leading term, or a negative coefficient for the leading term. Okay, so we see that the graph of this polynomial looks like this, and indeed it has the right end behavior. But right now we're focusing a little less on the end behavior and a little bit more on the middle behavior. And that middle behavior is characterized by lots of points, but in particular the x-intercepts and the y-intercept. Now from the factored form, which we see here, I'm just going to clear this so we can read it better. The factored form, we can easily see that we have 3 different x-intercepts, or 3 different zeros. One of them is at x equal to 0. Again, if we set y equal to 0 and then we use the zero product property, x squared equal to 0, or x plus 2 all cubed equal to 0, or x minus 1 equal to 0 would give us 3 solutions, either x equal to 0, which is right here, or x equals negative 2, which is right here, or x equal to 1, which is the third x-intercept right here. And then I've zoomed in at each of those graphs so that we can see the shape a little bit in greater detail. And so by zooming in, we see that this graph has kind of a flattening out. And so here in the case of this factor, this root, and the multiplicity of 3, which is coming from the exponent, we see that at a 0, or x-intercept, of odd multiplicity that is more than 1, so the multiplicity here is 3, it's odd and it's more than 1, the graph has a horizontal tangent. It flattens out here and looks like a horizontal line if we zoom in. The graph does not turn around. The graph crosses the x-axis, and the graph is flatter for higher exponents. So if this were an exponent of 5, we would have a more exaggerated flattening out of the curve. In the case of the x equal to 2, 0, or the x squared factor, we have the multiplicity is 2 here. And at 0 of even multiplicity, so 2, 4, 6, 8, etc., the graph has a horizontal tangent, so the graph looks like it's flattening out, but not as much as it did over here. And if we have an exponent of 4, or a multiplicity of 4, the graph would be even flatter. And same for an exponent of 6, it would be even flatter. And so we have a flattening out, which leads to this horizontal tangent. The fact that the graph looks like a horizontal line if we zoom in. The graph turns around without crossing the x-axis. It touches, but the graph doesn't go through the x-axis. And for higher exponents, we get flatter and flatter graphs at the 0, or at the x-intercept. And in this third shape, we have the factor of x minus 1 raised to the exponent of 1, and that exponent tells us the multiplicity. When we have a 0 of multiplicity 1, the graph looks pretty much like a line. The graph goes smoothly through the x-intercept. It doesn't have a horizontal tangent, which means it hasn't flattened out like in the other cases. The graph does not turn around like in the even multiplicity case, and the graph does cross the x-axis just like the other odd multiplicity cases. But we've kept this odd case separate from these odd cases because these ones have flattening out, whereas this case of the graph looking like a line does not flatten out. Okay, so let's use that information to match the equations and their graphs. This is a really good opportunity for you to pause the video and to take a look at matching them on your own and then check the answers afterwards. The first thing I did when I analyzed these graphs was to first look at the leading term of each of the polynomials, and then I came up with the end behavior. So I saw that x times x times x is x cubed plus dot dot dot. That just means that there's other terms when I expand from the standard form that I'm not representing. And then the x cubed has the end behavior of going left and down as well as going right and up. The next term I look at x squared times x because I would be expanding this binomial squared to get the leading term of x squared, again another x squared times x. That would give me x to the 5 with this end behavior shape. And I did that all the way through. X cubed times x would be x to the 5 plus lower ordered terms. And so I noticed that there are 4 odd behavior end behavior shapes and 4 even end behavior shapes. And it just so happens that I put all of the even ones across the top and all of the odd ones across the bottom. That was just a coincidence. So then I noticed I could use that to help me eliminate the graphs, and then I noticed that the A had to be one of the odd behavior for the ends, or odd end behaviors. And I also noticed that none of the graphs had a flattening out shape, and so that matched with this graph here. So I've put letter A to represent that equation. Then I took a look at part C. I noticed there was a cubic here, so I wanted a flattening out that would go smoothly, that would flatten out but continue to go through. And that only happens at this shape of graph. These turn around, and this goes smoothly through. So the only time at x equal to -1 that we had the cubic flattening out shape, which looks like this, either like this or like this, depending on which direction we're coming from, was here for C. Then I noticed for part B, or for this graph here, I had two turnaround and a smooth, so I had turning around coming from even exponents, and so that had to be x plus 1 squared, x minus 1 squared, and then x minus 2 to the 1. So those two came from these exponents, and then the smoothing, going smoothly through, was from x minus 2 to the 1. And here I noticed that I had a cubic at x equal to 1, and then I had smoothly through and smoothly through. So that alerted me to this exponent on that factor. Another thing to notice really is that all of these polynomials have the same three x-intercepts. So at -1, +1, and 2. So we couldn't really distinguish the x-intercepts to come up with the matching for the graphs. For the even cases, I noticed that I had only one cubic, and that cubic had to be at x equal to 1, and that cubic shape was right here. At x equal to 1 here, we're going smoothly through, so the exponent on x minus 1 would be 1. Here we would have an exponent of 2 on x minus 1, and here we would have an exponent of 1 on the x minus 1 factor. So I got that coming from here. And then for this graph, I noticed that I had a smooth, and a turning around. So at x equal to 2, I had to have an exponent of 2. So I looked for that, and this was my only case, and I just confirmed that these both had exponents of 1, which meant that the graph went smoothly through. For this graph, I noticed that there was one turnaround point at x equal to 1, and then smooth for the other two x-intercepts, and that corresponded to graph E, because the exponents are 1, 2, and 1. And lastly, I had turning around and smooth, and so that corresponded with this exponent on that factor for the root of x equal to -1. And so that's how I matched it all. If you're unclear, just double check again, go through and check Desmos as well to see what the equation and the graph connection would be. Now that we have some connection between the algebra and the graphs of polynomials, we can do some application of polynomials. Here we have a question that talks about the shipping rate of a rectangular box at the post office being based both on the box's volume and on the sum of the three dimensions. We want to keep the cost down, so we want to be cost effective. So we want to design a box that has the maximum volume. We want to be able to send as much stuff as possible. And we also have a constraint that the box is twice as long as it is tall, and we want to keep the sum of the dimensions, the length, the width, and the height, at 12 centimeters. So what are the dimensions of such a box? Well, here we have some steps for problem solving. And so one of the things to keep in mind is that we are going to introduce non-x and y variables. We will introduce x and y later on in step 3 when we have a single input and a single output. But at the beginning, we might not only have one input and or one output. So we're not going to use x and y until the point where we do have only one input and one output. Okay, so we'll start in step 1. We almost always sketch a picture because a picture gives us a lot more information well, in few words. So when we've got a word problem, we can simplify or streamline or convey a lot of the words in the picture. And so we're going to have a box, and we want it to be twice as long as it is tall. So we might call the dimensions height, length, and width. And from here, we have some information about the height, length, and width, so we're going to define them later on in other equations. So step number 2, we can write the equations. We know that, let's highlight this actually so that it's a bit clearer. And it says we want to design a box that is twice as long as it is tall. And so that equation, or that sentence, can be rewritten as an equation I'm going to call this number 1. Twice as long as it is tall. So that means the length is equal to 2 times the height. We also want to keep the sum of the dimensions at 12 centimeters, so that's another equation. And so we can call that equation 2. Equation 2 says that the length plus the width plus the height is equal to 12. And we also know that the length is equal to 2 times the height. So wherever possible, we should eliminate other variables. Now, keep in mind that I said we don't want to use x and y at the start because we should have only one input called x and only one output called y. Right now we've got 3 variables. Maybe we're not clear if they are input or output variables or a combination, but we know that we at least have more than 2 variables. And so because we've got more than 2, we're not sure who is who. So don't use x and y yet. Now, whenever we solve problems, we need to have an idea of not only what we're working with, but where we're going. And so the question is asking us to find the dimensions of a box, but it says of such a box. It's a box that has maximum volume. And so we want to come up with the volume of the box. And that's going to be our equation 3. So I think we've got all the other conditions. Such a box means that it is twice as long as it is tall, and that the dimensions add up to 12 centimeters. So the third equation is a volume equation, and volume depends on length, width, and height. So volume is a function of 3 input quantities. And so now we can actually see that we've got 4 variables, and then 3 of them are inputs, and 1 of them is an output. But eventually we're going to want only 1 input and 1 output. And then we're going to come up with a graph with only 1 x and 1 y. Okay, so the volume, as we know for a box, is length times width times height. And in step 3 it says to write a single function, and so we want a single function of a single variable. That means that we want to eliminate all but one of these input variables. Since we know that length is equal to 2 times height, we can rewrite equation 2 and eliminate L. So we can replace L with 2h. And so we have that 2h plus w plus h is equal to 12, which we can rewrite as 3h plus w, or w plus 3h is equal to 12. Now, we also want to, instead of having an L here, which we can replace with 2h, we want to get rid of either w or h, and we can easily rearrange this equation to solve for w. So if we do, we know that w is equal to 12 minus 3h. So what we've done here is come up with 2 equations that eliminates L in favor of h and eliminates w in favor of h. So we're going to replace w with that expression as well, and then we will have volume as only a function of a single input, h. So to write a single function, we will have volume of h is equal to length, which is 2h, times w, which is 12 minus 3h, times h. And so now we can rename h with x, and y is going to be the volume, or the volume as a function of h. And so our equation is going to say y equals 2 times x times 12 minus 3x times x. And so what we have here is a polynomial in factored form. We can rewrite it a little bit, and I'm going to use the space up here because I'm running out of space. And I can see that y is equal to 2x times x, so 2x squared times 12 minus 3x. And I know that 12 and 3 have a common factor of 3, so I'm going to factor that common factor out, and I'm going to get y equals 2 times 3, which is 6x squared, times 4 minus x. So just to be really clear, I took out a common factor of 3 and was left with 4 minus x here. Then I took the 2 and the 3 and I multiplied them together. So this is my cubic polynomial. It has a leading term of 6x to the exponent of 3 times a negative 1. So negative 6x cubed plus dot dot dot. And I know that the end behavior of that graph will look like that, but I'm going to use technology at this point. Step 4 says to determine the domain. We really want to know what has to be true about all of the input values, and we know that to come up with a box, that the width has to be greater than 0, and the length has to be greater than 0, and the height has to be greater than 0. And because we know W, L, and H in terms of H, we can rewrite this to say, I'm going to run out of room here, so I'll put it underneath. W is 12 minus 3H, which must be greater than 0. And if we solve that, we get 12 must be greater than 3H. And therefore, dividing by 3, we get 4 must be greater than H. And we also get that L, which is 2H, must be greater than 0, and therefore H must be greater than 0. And, well, the last one, H must be greater than 0, says the same thing. So we can condense these two statements into one statement that says H must be greater than 0. And we have that 4 must be greater than H, and H must be greater than 0. If we plot those values on a number line, if this is my H number line, and keep in mind that H is now equal to X because we renamed using X and Y, just put that in here, then we know that H being greater than 0 is, let me put that in green, here's 0, and H being greater than 0 is all of the values to the right, and H being less than 4 is all of the values not including 4 and to the left. And so we want H values that are both in the blue set and in the green set. In other words, we want the values of H that are between 0 and 4. So to come up with the domain of our graph, we know that H or X has to be between 0 and 4. So the domain is the set of values that make sense to the algebra, but also make sense to the real world problem. So 0 is less than X, which is less than 4. Okay, we have a domain, and we're now really ready to come up with a graph using technology and to ultimately solve the problem. Well, keeping in mind, we wanted to find the dimensions of the box that had the sum of these dimensions to be 12. That was twice as long as it is tall, but ultimately that had maximum volume. So the maximum volume part tells us that we're looking for the turning point of the graph. And the graph that we need to plot using technology is y equals 6x squared times 4 minus x. So we've modeled the box, we can use technology, and then we can answer the question. And so let's just go to Desmos again and come up with a new equation. We have y equals 6x squared times 4 minus x, and that graph is only valid from 0 to 4 for x. And this is how you write the domain in Desmos. You use these curly brackets, and then you just put from 0 to 4. And so we see we've got this graph here. I'm just going to go back to a home window and then maybe customize my dimensions. I don't know what that maximum volume is, but I'm just going to take a stab that it's maybe about 30. Nope, that's not big enough. Maybe 50, still not big enough. Let me go to 100. Okay, that might be, so I see that it's under 60. So I'm just going to go to 60 so that I don't have such a big window. And then maybe my y step, I could put it at 2 or 5 or something a little bit smaller. Okay, so I have my graph like that. I could take a screenshot of that graph just so that I have all the information that I want. And I can click on that maximum point, and then I can add that screenshot to my solution. But really I'm interested in the maximum point. And in fact, I'm not interested in both coordinates of the maximum point because I know that this graph, actually let's do something here. We can go to the label and we can put X is the height of the box and Y represents the volume of the box. And there are lots of different volume values, but there's only one maximum volume value, and that's the one answer that we're interested in. So I'm just going to take my labels like this and capture that and input it in my solution. So now I see that the x-coordinate, or the height of the box that leads to the maximum volume, is 2.667 inches, and the maximum volume is 56.889. And so we're really just going to go back a slide, and to answer the question, it didn't actually ask to come up with the maximum volume, it wanted the dimensions. So I'm more interested in the x-coordinate here, which represents the height. So the height is 2.667, and I can say to get maximum volume, so we answer in a sentence here, to design such a box, and remember the criteria were maximum volume, the sum of all the dimensions equal to 12 inches, and the length being twice as much as the height. We need height, well, let me just put it like this. X equal to height equal 2.667 inches. We need the length, which was equal to 2 times the height, which is equal to 2 times x, is equal to 2 times 2.667 inches. We can work that out in a minute. And we need the width, which is equal to 12 minus 3h. And since h is the same as x, that's the same as 12 minus 3x, which is 12 minus 3 times 2.667 inches. And we just take a calculator, we work out those numbers. And we have the 3 dimensions that we need for the box. So use this template with these 6 steps and really make sure to define non-x and y variables until the point where you have a single function with a single x and a single y, a single input and a single output. That's because you can only have one input and one output along the graph, and if we had used x and y earlier on, then y might have represented the length, for example, and then later on when we try to represent the volume, I think I called this the volume, we don't want the height to be called y and then the volume to be called y. It gets really confusing then. So volume is y and x is height. Okay, well there you have it. Just looking at different applications of polynomial functions, but we can start off by understanding the linear factors and the zero relationship to help us come up with the graph. Thanks for checking out Raylene Maths.